Okay, so welcome everyone. Today we will do centroid decomposition. So are you able to see my screen?
Yeah,
Okay. So these are the topics we will be covering today. So we will be doing what is centroid and how to find it. Then we will move on to centroid decomposition, its construction in NlogN. Then we will look at properties of centroid tree, and then we will do some problems. I have prepared 5 problems, but we will see if time permits or not. Okay, so let's begin with what is centroid and how to find it. So centroid is a node in a graph such that if you remove this node, then the graph breaks into components so that each component contains less than n by 2 elements. So suppose this is a node u, then I call this u as a centroid of my tree. Sorry, I use word graph. So these all are defined in tree. So I call this as centroid of my tree. If I remove this node, then the remaining components that will be found will have all less than n by 2 elements, or you can say less than equal to if there are even number of elements. Then I say that this node is a centroid of the tree. So our first claim is centroid. There is a centroid for every tree. Centroid is always there. So why it is so? So suppose okay. So let's first consider how to find the centroid. Then we will prove that there always exists a centroid. So how to find the centroid? So if I start from a random vertex and then look its subtrees, then if all of them contain less than n by 2 elements, then I am done, because I satisfy my this node satisfies this definition of the centroid, so it is the centroid. Suppose there is a subtree, let's say this one, and it contains greater than n by 2 elements. Suppose, then since total nodes are n, and this one contains greater than n by 2 elements, so com- all the remaining nodes will have less than n by 2 elements. So let's suppose it is connected by this node and then this. So our centroid will lie in this subtree. It can't present a here, because all the size is less than n by 2, because its size is greater than n by 2 and total nodes is n. So we move to this node and then search again. So we keep on doing this, and eventually we will end up with a single node, because at first I have n nodes. Then for this subtree, this is this subtree, and these all have less than n by 2 nodes, so I don't have to come back to this node again. So once I come to this node, then then I will not come to this node. So now I will consider only this tree. So initially I had n numbers of nodes, then I have these number of nodes, and so it would be less than n, so the number will reduce. So eventually it will come down such that all the subtrees will have less than n by 2 nodes, because the numbers are continuously reducing. So it must be even if it is a single node, it must end to a centroid. So for example, if I take this one, and then what we do is first assign the size of the subtrace. So it is 1, it is 1, it is 1, it is 1, it is 2, 3, it is 3 plus 1, 4 plus 1, 5, it is 3, it is 1, 1, it is 10. Now, so the first step is run DFS and assign the sizes. Size. Second step is start from root. Now, say I am at this position. Now check for the condition. So total number of nodes are 10. Now 10 by 2 is 5. So in this tree, the condition is satisfied. So this is the centroid. Let's suppose I have this node also. So it would be 1, it would be 2, it would be 6. Yes. Now the number of nodes are 12 by 2 is 6, and this part part does not satisfy the condition, so our centroid will lie in this part, so we move to this node. Now we again check. Now while checking this, we don't need to consider this node, because we already know that all these nodes will have less than or 12 elements, and we don't want to consider this. So we will check only its subtrees only. Now check for its subtrees. Or both of its subtrees contain less than n by 2, which is 6. So this is the valid centroid of the tree. So we end here. So start from root. Check check for the condition. If it satisfies, then break. Otherwise, move to largest node, largest heaviest node. Okay, so this is the algorithm for finding centroid of the tree. So I will show the code of finding centroid. So this is the code. So we initialize the centroid by root, and then we check. So we have done the DFS initially. So the DFS is for assigning the sizes to its subtrees. Then we have doing we are initializing the centroid by root, and then for each subtree we are checking if its size is greater than by 2 or not. If its size is greater than by 2, then its centroid will lie in the subtree only, so we'll recurse. Otherwise our centroid is the root only, and then we'll return. So this is the code for finding the centroid, and this is in O of n. So this is O of n algorithm for finding centroid of the tree. Okay, so is it clear, the centroid, how to find the centroid, and the O of n complexity? So the now the second thing is the centroid always exists is pretty much simple from the fact that we run the algorithm and the algorithm will terminate, because you run the algorithm and initially you had n elements, then you will have n minus x, say, then n minus x minus y. So you will eventually have a vertex which satisfies the condition, because even a single vertex satisfies the condition of a centroid. So your algorithm will terminate. So centroid always exists for every tree. So this is a property that the centroid is always there for a tree. You can have multiple centroids for a tree. For example, if you have this tree, then the centroid is this also and this also. If you have this, then both of them are centroid. So the centroid is not unique, but it is always there. So this is about centroid. Now we will come to centroid decomposition. So okay, so we'll consider the above example. Okay, so in this case, the centroid was this node. So this was our centroid. Now, what is centroid decomposition? You are given a tree. Now you find the centroid. So you will have vertex u, which is a centroid, and then it will be like this. So you make this root, and it will be like this. So in our case, it will be like this one. The second part would be this one, this and this. Now, for each of these subtrees, you again do the same. You find the centroid, and let's say this is the centroid. See, centroid is the centroid can be the different node, which is the connecting node, and you connect this to this, and repeat this. So I will show the example. So this was our centroid. Now, let me label them. So node 3 was our centroid, and then we had node 1, 2, 4, 11, 12, then 5, 6, 7, 8, 9, 10. So after one step, we so this is the tree we have formed. So this is our centroid, and we have so this is the original tree. Now we repeat the process for this part, this part, and this part independently. So this one, so its centroid will be this node only, because total nodes are 3, and one is less than 3. One is less than 3 by 2. It is also less than 3 by 2. So it will remain same. For this node, total nodes are 1, 2, 3, 4, 5. and these are three nodes, so it is greater, so the centroid is this node. So it will be like 4, and then 1 2 4 11 12. So this is the tree formed after doing centroid decomposition of this part, and now we join the centroid of this tree, which is 4, to this root. So this this is our centroid of this subtree 5 6 7. We join this with this, and then we are left with 6. 6 is the only node in the new tree. So it is centroid itself, so it is joined to this node. 7 is joined to this node, and same is for 8 9 10. So you don't see the difference in these two trees because they contain three elements. But consider this subtree. This is the node which is the centroid of this subtree. So we connect this node with this node. So this is our centroid, and this was our centroid. So we connect both of them, and then we recursively do this. So we had this. So 1 is the centroid of this part, so we connect 1 with this. 11 is the centroid of this part, so we connect 11 with this. 12 is the center of this part, so we connect 12 with this. So that's how we have formed this. So this is centroid decomposition. We have decomposed the tree into, so all these are centroids of different components, right? So this was the centroid of our original tree. This is the centroid of the this component. This is centroid of this component. This is centroid of this component. So all the nodes are centroid of their respective subtrees. So this is centroid decomposition. So is it clear what is centroid decomposition? So decomposition of trees such that all the nodes are centroid of their subtrees. So now I have a tree. This is the centroid decomposition of a tree. So this is called a centroid tree. Let it be this. So the first property is height. So consider this. So initially my all my nodes were n nodes. Then what did I do? By the definition of centroid, all the subtrees contain less than n by 12 elements. So since this is the centroid, so all the subtrees will contain less than n by 12 elements. So this will contain less than n by 12 elements. So maybe this may be not the valid centroid tree, but I am just showing. So this contain less than n by 2 elements. This contain less than n by 2 elements. So at the this level, total n nodes are there. At this level, how many nodes its subtree contains and less than n by 2 elements. So at this level, less than n by 4 elements. At this level, less than n by 8 elements. So it will go until how many levels? So n divided by 2 to the power x less than 1 equals to 1. So 2 to the power x is n, x is log n. So that's why we say the height of the centroid tree is maximum log n. So I will repeat this again. Initially you had n nodes for all the trees. Then at the first level, so this is the zeroth level. At the first level of the centroid tree, so this is now the original tree. You will have maximum n by 2 elements for each subtree. So less than n by 2. This will have less than n by 4. This will have less than n by 8. So it will go until 1. So how many times it goes? So n divided by 2 to the power x is 1. 2 to the power x is n. X is log n. Okay, so the centroid tree. So this is at max because uh, this is less than n by 2, not exactly n by 2. So the centroid tree has at most log n height. So this is the most important property of centroid tree, that its height is at most log n. Irrespective of the height of the tree, the height of the centroid tree will be log n. So let's take an example. So suppose your tree is this normal tree with height n. 1, 2, 3, 4, 5, 6. Now I want to do the centroid decomposition. So what will be the centroid? This can't be a centroid. This can't be. So three elements, 6. Yes. So three will be the centroid. Now it will connect to the centroids. So for this part, two is the centroid. So it will connect to this. And for this part, one is the centroid. So it will connect to this. Now for this part, five is the centroid. So it will connect to this. And for these two parts, only four and six. So they are single elements. So this is the centroid tree of this tree. So you will see that if its height is n, then also it will have height at max log n. So this is centroid decomposition. So we have seen that the height of the tree is at max log n. So now how to build the centroid tree? Construction of the centroid tree. So one way is to, yes, yes, anyone wants to say anything? Okay, so now one way is to just do what we were doing on paper. So find the centroid of the tree. So it will be in O of n. Then remove the node, remove the node, and find the centroid, and do the same for uh, all the subtrees, all the trees formed, and then connect their centroid to this centroid. So this looks of n square because uh, you see you find the centroid in O of n, then breaks the tree, then breaks the tree into number of components, different components. Each will also run the algorithm in O of n. So at max they can have n minus 1 elements. So from n to n minus 1 you have O of n step complexity. So overall you can have n square. So this looks n square. So I proved that why it looks n square, because you are having n minus 1 steps, and at every step you are using O of n, O of n time to find the centroid. But the fact is that this algorithm is n log n, this same algorithm, and this is based on the property of the centroid tree that the height is log n. I will prove that the complexity is n log n. So construction in n log n. So proof. So the construction clear? We just so the process is this: find the centroid, remove the centroid, do the same for all the trees formed, connect their centroid to this node, the centroid which you have found for the entire tree, and repeat the process. So do this only, and I will prove that the construction will be NlogN.
So if we come from a parent to a child, how do we write that? Like, if we store it in an adjacency list, then how uh, do we reinitialize everything, like the array for checking which nodes are visited?
Yes, you can pass a visited. I will show you
So
by
this
code.
like this assumes that the current node is the centroid. Let's say this was not the centroid and we move to a child of this node. Then how do we
No,
take care of?
no, you first find the centroid of the tree.
Yeah.
Then, so this is the centroid I know because I have found the centroid. So
Okay.
what's your doubt?
Yeah. So for every child, it's fine. But let's say we also have to include the parent also, right?
Yeah, so parent will be the centroid of the entire tree. So first I have found the
No, no,
centroid of the
no.
entire.
This node's parent.
It's not parents. So it will be it doesn't have any parent because it will be -1, let's say.
Okay, you changed the tree. Okay. Okay.
Yeah,
Hmm.
yeah, the tree has changed. I will show you by code how do we do that, or how do we implicitly remove the node. We don't we don't do remove in we don't erase the node. We just keep a visited array. For illustration purpose, I am using the word remove. I will show you by code. Okay. So the proof in that it takes nlogn is, so you run of n for finding centroid. Why? You run a dfs for the tree for assigning sizes. So you visit each node. Okay. And then again you come to this, then you may come to this, you may come to this. So you can say that you are visiting each node twice in this uh, tree. If I'm having a tree, then you are visiting each node twice. That's why often. But overall, for the whole tree, how many times you are visiting each node? So how many times a node will be visited? So it will be same to answer as how many times it will be counted in the DFS. So if I have a centroid and I break this component, then I will run DFS for this component, and again I will find the centroid as this. I will break again this, so I will run the DFS for this. So how many times this will be in a DFS of some node? This will be in DFS of some ancestors of it only, right? Because every time uh, I find a centroid and I remove them, then in the centroid tree, wherever, irrespective of wherever it is present, it will be the centroid. It is the centroid for the whole tree. So in the centroid tree, this will be some ancestor of all these nodes. So this will be some ancestor of all these nodes. So this particular node, if I want to talk about this particular node has been visited how many times? It is visited often times, but often means what? How many times it is? It's not. Oh, sorry, not often. How many times the DFS is called for this node? It's visited that many times, and for each call there is an ancestor present. So the number of ancestors will be the count of the number of times then this node is been visited, and by the property of centroidity that its height is log n, the number of ancestors are also at max log n. So this node is visited log n times. So total n log n will be the complexity. Is it clear? Why n log n? So we do the same process, but earlier we were thinking that it would be n square, but the actual complexity is n log n. So the algorithm is simple where you just do a recursion. You just find a centroid and then you do recursively for all the subtrees, and then you connect the centroid to the centroid of all the subtrees. So this is n log n. Now I will show the code of the construction. So this is the class. So this is the code for finding centroid. This I already explained. So this DFS is it is assigning the sizes to all the subtrees. So subtree so size of one to leaf, then it's storing the size of its subtree, and then this function get centroid is you feed the graph in it, and it will return you the centroid of the entire. So yeah, I say graph. So if you feed the tree, you'll get the centroid of the entire tree. So this function is giving you the centroid, and this is the recursive function which I explained, that this function is the main code for centroid decomposition. First we are finding the centroid. So for finding the centroid we have to assign the sizes. So we are running the DFS, and this function gets centroid. This is the center of the entire tree. Now how do I remove the centroid is I am using a visited array which keeps which is true when the node is visited. So this node I want to remove this, but I don't erase in uh, I don't erase in vectors. So I make a visited array, and this will keep that this will remember that this node has been visited, and don't visit to that node while doing Davis. So so this line, so we keep this. Then we move to all its children, which are so we the all the children separately do the centroid decomposition, and then all they are returning is the centroid, which I have to connect to the main centroid. So this is the main centroid CTR, and CH is the centroid of the child, and I am pushing the uh, CTR, and I am pushing the vertex into this, so that to build the tree basically. And this is the parent array, so parent of this is CTR, and it's returning the centroid. So this whole function is what it is doing is doing the centroid decomposition of the tree, and it is returning the centroid of the overall tree. Now how this comes into play is you can see here. While doing DFS, I am checking if it is visited or not. If it is visited, and then ignore it. While finding the centroid also, I am doing the same. So we can remove the centroid by using this line. So is it clear how do we find the centroid? How do we construct the centroid tree?
Where did you remove the original child from the adjacency list? I mean, you added the
Yeah.
new centroid.
So this line is
No, no, this will ensure that we do not visit it during the DFS, but we have to modify the tree also, right?
no, no.
Adjacency list also.
See, you have this. So let's say these these are my nodes. So one will have 2, 3, 6. This is the adjacent list. Two
Hmm.
will have nothing. Three will have 4, 5. 6 will have nothing. Now one will have 2, 3, 6. So what I'm
This
doing
is the
is,
agency. Two will have
yeah,
nothing in the adjacency list.
yeah. So it will have one, but since I am using the parent also, so you can I am for illustration purpose I am using this. Okay, if two will have one also.
I think the visited array is for just centroids only. It's not getting
Yeah, it does not
updated in
visit the
DSS.
centroids
No, no, no,
again.
no. So the visited will mark the, so this will mark this. Now when I come to this, the visited array is true for one. I will not come to this while doing DFS. So this edge is been removed for me, right? I will not come to
Visited
this.
Yeah,
array.
DFS
Visited
in
array
DFS
is the
visited array
visit
is not
array
getting
for
updated.
centroid tree. For
No, no, no,
centroid
no,
tree.
no. In DFS, visited array is not being updated because I don't want to update this.
Yeah, yeah. No, no. We are
Yeah, so
talking
his
about
question
same.
was different.
Okay, okay.
We are
So is
talking.
it? Yeah, is it clear?
Yeah.
Okay. Uh, the one who asked, is it clear for you?
No, I was just asking that. So for this new subtree, 4 will be centered, and I see that you have pushed the 4 into the adjacency list of 1 at the end, right?
I have pushed the 4 into adjacency list of 1. So the
Yes.
graph was initially, so
But
I
where
am
did
not
you
pushing.
remove? I mean, I'm not getting where did you remove that edge 1, 2, 3? I mean, I'm getting that when you go to the subtree of 3, you won't visit 1 because you have marked it as true. But you're saying that we are modifying the tree also. That's why you pushed 4 into the
So
adjacency list of 1.
no, 4 into the adjacency list of 1 by,
Can you show the code again?
okay,
On line 43, I'm saying.
943. Okay, so this is the centroid tree. So
Okay, so
this,
you're making a new tree. Okay,
yeah,
okay,
yeah,
fine.
this is the centroid tree and this is the graph.
Okay, okay, okay. Yeah,
Yeah,
okay, fine.
okay. So 4 is the centroid, so it should be pushed in this because we are making the centroid tree. Okay,
Okay.
so the construction is clear. So, and I have already proved the complexity in NlogN. So now we'll move to the properties. The first property I've already
Can
explained.
you explain the
Yeah,
proof
yeah.
of login times again once, like really
Okay,
fast? I just wanted to.
okay. So is it clear that the height of the tree is log n?
Yeah.
Okay. Now consider how many times. Okay, I will explain the code. So consider how many times these two codes will be executed. These will determine the complexity of the overall code, right?
Yeah, I understood how you said it appears to be O of n square, but I just want to know how you showed that each node will be visited at most O of log n times
Okay,
or log n.
okay, okay. So now consider finding a centroid. Say you have these three subtrees, and it will have many nodes in it. Let's talk about this node, how many times it will be visited. Now this node will be visited this time because I am doing DFS this time for every node, right? Now I am saying whenever I am doing DFS for a node means for this tree, I am doing a DFS. Then every time this will be an ancestor of this node U in the centroid tree. So if this node is V, then V will be an ancestor of U in the centroid tree because what will I do after this? I will uh, I will do this. I will repeat the same process irrespective of the position of U. U will come to some node, then it will come to some node, then it will come to this node, right? This has to be the ancestor of this. So V is the ancestor of U, some ancestor. And every time I do a DFS for U for V in which U comes, I say V is always the ancestor. So how many times U will be used in a DFS? The number of ancestors it has,
Yeah, I got it.
and
That's
the
it.
number of ancestors are log n.
Hmm.
So for every node, I just visit log n times, so n log n complexity. Okay,
Got it. Yeah.
okay. So now we'll do the properties. So there are only two properties, uh, which are the height of the tree, which I already proved. The height of the tree is log n, and the second thing is yeah, the second thing is very important property. So consider any path in the original tree. Let's say A to B. Then in the centroid tree, how will it look like? It can have it can be anything. So let's say A is some here and B is here. Now the claim is let so this is the LCA of A and B in the centroid tree. Let it be C. Now the claim is C is present in between this path. This is the property. I repeat again. For any path a for any two nodes a and b in the original tree, this is my original tree and this is my centroid tree. Now C is the LCA of A and B in the centroid tree. Then my claim is C will be present in between the path of A and B. So I can write the properties like distance of A comma B is distance of A comma C plus distance of C comma A or B comma C. So this will be present in between the original tree. So this is the claim, I will prove it. So is it clear the property? So I will prove why it is so, and this is the property which we use in every question. Only these two so only these two properties are there, and this is the basically property which we use every question. So I will prove that. So we have to prove that the vertex C, which is the LCA of A and B, will be present in between the path. So okay, I have closed this. So now consider centroid decomposition. If I decompose this, these two are some subtrees T1, T2. So this is my tree. Now if I decompose this, then T1 and T2 will be present like this in centroid tree. So let's suppose T1 is this and T2 as it is. So 1, 2, 3. So it will be like this. So 3 and T2, 3 and T2 will be in the different components in the centroid tree because they have been they were connected by this centroid, and now they are in different components of this centroid tree. So this must be the LCA, right? Because they are in different components, and LCA is the first nearest node which we, because this node is same for both, and they are in different components now after removing the centroid. So because before removing the centroid, if the centroid was this, then this will be in same component, this whole. So it was like some ancestor of this. But now when I remove these two, then this is centroid, and it would be the LCA because now they have been disconnected. And since they have been disconnected in the tree, and earlier they were connected, so this must be the LCA, right? Because LCA is what? If you LCA is if you move upwards, then this is the first node which connects them, and afterwards also you are connected. So before so in the centroid decomposition, the first node which disconnects these two nodes is will be the LCA, and so this will be the LCA. Now this is present in between this I have to prove. So the first node which disconnects them will be the LCA. This is the definition of LCA, I guess. The first node which disconnects the tree. Now this node will be present in between the path. So this is the centroid tree, and this node is present in between the path of the original. So let's suppose this node is present here. Let's suppose this. Now when I am doing centroid decomposition, now when this node becomes centroid, this breaks all the components, right? So A and B will be in same component of the centroid tree. It would be like this. But since A and B are in different components, so this must be present in between A and B so that it could break them, right? Is it clear? I will repeat again this thing. So we have the path A and B, and I and A and B is present somewhere in this centroid tree, and our claim is this node C, which is the LC of A and B, lies in the path from A to B. So what is our proof? Our proof is consider the process of centroid decomposition. So when will this happen that A and B will be disconnected in this tree? So initially they are connected. So when will this happen that A and B will be disconnected? So when there is some node outside this, then it breaks the whole component, including A and B. So this will not be the case with the node with in the outside of the path from A to B. So there must be some node in between A and B, which became centroid now, and they it disconnects this. And now why this is the LCA? Because this is the first node which is disconnecting them, and the first node which is disconnecting them will be the node which is present if I which is present here, which is the nearest node from below from A to B. This is the first node which is the same for both of them. So that is the definition of LCA. So that will be LCA. Okay. So we will see from questions that why this property is so important. So if you have any doubts in this property, then ask. Otherwise, you will not. If you don't understand the proof of this for now, you can just remember the property that for every path in A to B, the LC lies between them. Just remember this. You can analyze the analyze this in your pace after this. But for now, because we will be doing questions based on this, just remember that for any path between A to B, the LC lies between them, and the any node which is outside of A and B will be the ancestor. So this property we will be now doing questions. So read this problem. Should I read or Xenia, the programmer, has a tree consisting of n nodes. We will consider the tree nodes indexed from 1 to n. We will also consider the first node to be initially painted red and the other nodes to be painted blue. The distance between two nodes v and u is the number of edges in the shortest path between v and u. Xenia needs to learn how to quickly execute queries of two types. Paint a specified blue node in red. The second one, calculate which red node is the closest to the given one and print the shortest distance. Your task is to write a program which will execute the described queries. This is the input format. NNM. So you are given a tree and all the nodes are initially red. You are having two queries of two types. First one is paint any node in blue. The second is calculate which is the closest red node to the given node. So you are given the node and you have to tell which one is the closest red node.
We just need the closest red node to each centroid, right? Uh, then we can check every ancestor of the current node and because and check the answer. right?
But why should it work?
Yeah. So if we have like, let's say we are able to process the query one, let's say for two, if we only like we calculate for every centroid what is the closest red node. Okay. Then let's say we have a node and we need to find the closest red node. We'll just traverse all of its ancestors and check the distance between like from this node to the ancestor and then from the ancestor to the closest red node. This
This
this will
this
be
will
the
this will this will be the okay. Okay. Let me ask you one question.
hmm,
If I change from min to max, will your solution work?
yeah. No, maybe not. Mm,
I think first I have to explain the solution because others might not be getting this, and then we will discuss this if we change from min to max. Okay. So the solution is your solution is right. So what we do is we build the centroid tree first. Okay. So why we are doing this? I will. Okay. So why we are doing this? You have to tell which red node is closest to the one and print the shortest distance. So let it be any node. So this is my current node A, and I have to tell the closest red node. Let it be A to B. Then from the property which I have discussed, the path property, there must be some LCA which is present between A and B, and the distance between A to B will be equal to distance from A to C plus distance from C to B. So for all the paths from A to B or from A to any node, there will be some LCA present between them, right? So I can decompose the distance from A to any path as distance from A to LCA plus distance from LCA to any node B, let's say. So this is why we use centroid tree in this problem, because uh, we want to get the distance for we want to somehow get the distance for all the paths. And what is common in all the paths, that they will have some LCA in between. And since in the centroid tree the height is log n, so the number of LCAs will be log n because the LCA is the ancestor of A. So I can iterate over all the nodes which are my ancestors and take this node to be my LCA and keep this distance, and then distance from this node. Take this node to be my LCA, keep this distance, and distance to my other node. Take this node, distance to my other node. Now I have to find the minimum distance. So what I have to do, I have to just so this distance is constant. A to LCA, the distance is constant.
so when we take the other like uh,
Other node, yes,
no, so we have for each centroid will like which is not part of this subtree, right? We have to choose the node,
yes,
the
yes,
closest red node.
yes, yes.
Okay, yeah.
So, but in this, okay, I will. So that's why the min max was not working here. I will explain this. Okay, so if I am at this node, I will take this node and take the distance. Let it be c. Distance from A to C will be a constant. And now what I want is the distance from C to any node which is minimum, but I don't want the this node to be in this component base, because I want these two nodes, because I want the LC of A comma B to be C for my property to be valid, right? LC of A comma B must be C. So if I am here and this is C, then B must be present somewhere in this part. B can't be present somewhere in this part. This B can't be present here because otherwise the LC won't be C. So, but ensuring this could be a little tedious, and the solution which Kumar proposed was that just take the minimum from this node. So it could include the distance from this also, but just do this and you will get the answer is right. I will explain why, because in this question I am asking about minimum and it won't affect the minimum answer. That is the crux of the problem. So consider this A and consider this node B. This is the centroid ray, remember. And now I am at this node C. Now I have gone to this. So this distance I am adding distance of A comma C plus a distance of, let's say, for all the nodes in C, the minimum distance it is having is to node B. So I'm adding distance of C comma B and I'm getting this answer. So it will be wrong because it won't correspond to any valid path, because LC of A comma B is this node which is D, but I am adding the distance from this to this. So how will it look like in the original tree? Let's look this. So this is A, this is B, and this is C somewhere present. Now any node, so sorry, this is not C. This, since this is not LC, this is D. The LC is D, and now the ancestor. I already told that the ancestors will lie outside. So this is C. Now what I am doing is let this distance be K. This is K1. So what I am doing is distance of A to C, which is K1, plus distance of B to C, which is K plus K1. I'm adding this, which is not a valid distance because the valid distance is K, but I'm adding K plus 2 K1. But since in this question I am only asking minimum, so it won't affect the answer because I will get a case where I will get the answer as K, because I will eventually I am doing for all the nodes, so I will do for this node also, and and when I do this for this node, which is the LC, I will get the right answer. So I will get K at some time for sure, and this and by doing this invalid query, I am just adding the larger answer, so the minimum won't be affected. But if the problem were like calculate the maximum distance between these two nodes, then I may get the invalid query and I will give you this answer. But this don't correspond to any path, so this will be wrong. So why it worked for minimum and why it won't work for maximum? Is it clear?
Yeah, how do we handle the updates though?
How do we handle the latest
Updates.
updates? Okay, okay.
Yeah.
So this is for querying. Now what we have to update is, so what we are storing is that we have to update. So what we are storing is in every node of the centroid, we are storing the minimum distance just. And for update, let this node is made red now. Initially it was blue, so it will affect the answer for all its ancestors only, right? So I will go to each ancestor. Since all the ancestors are so the number of ancestors are less than log n because the height of the tree, I will go to each ancestor and will update the answer of them. So answer of their ancestor, let it be u, will be minimum of answer of u, comma distance from u, comma let my current node this be cur. Okay, so this is the update. And okay, so one thing, how I am finding a distance is using LCA. So LCA in the on the original tree. So in log of n, I am finding LCA using sparse table kind of thing, right? So because so else so this I am assuming that you know before that distance from A to B is distance from, so height of A plus height of B minus 2 times height of A to B. Sorry, LCA to height of LCA. This is LCA of original tree. don't confuse it with the centroid tree. Okay, so this I'm assuming that you know. Now, is it clear? Yes. Kumar, you asked how to update.
Yeah, got it.
Okay, so this was a problem. So, do I need to show the code, or would it be fine? I have already did, so I can show the code also. But you won't understand much from the code. So do I need tell if you need to show the code or not? Okay, I will show.
No, I I don't think
Oh,
code will be helpful here.
okay.
Hmm.
So the question is done. So we'll move to another question. If you have any doubt, you can ask. So we have used the property of the LCA that the LCA will be in between the path and also the height of the node, height of the tree that it will belong in. Now we'll move to another question. So read the problem. Consider a tree with n nodes. Alex chooses a node V as a starting point and then travels over k edges. The resulting path consists of k plus 1 nodes. Alex then builds an array of size k plus 1 using the labels of the nodes and counts the number of inversions of this array. An inversion is pair ij such that I is less than j and ai is greater than aj. You don't know the starting point of the edges table, so you should find the sum of the number of inversions for all the possibilities. Nk is 10 to the 5. So what the question says is uh, Alex choose. So you choose any node, and for all the paths of length k, you find the number of inversions and add it to the answer.
Is V given or like any node
No,
V?
no, no. You have to add the answer for all the nodes. So for all the nodes, add the
We
answer.
start from a node and we travel k edges. We have
Yes.
k plus one nodes and find the number of inversions in the indices of
Yeah.
the
Yeah,
path.
yeah, and the edges you travel is also random. Like you do for all the possibilities. So for any path of length k, you so for all the paths of length k, find the number of inversions and then add to the answer. So this is the problem. So first think what will be the answer for a single path if I give you a single path. What will be the answer? So the number of inversions would be how many inversions you are having because if I okay do you want to think for a minute or should I go ahead?
It should be the total number of inversions possible, right? Like,
Yeah, total number of inversions.
yeah, it should be total, like for a single path, it should be the total number of inversions possible in a array of length k plus 1.
uh, in an array of length k plus 1 total number of inversions. So
Yeah,
total
that
so
is,
what
how much is it? NC2.
no why
Because, like, you'll start from the first node, and the only two possible paths are first to last and last to first.
yes
So, first to last should be one part, and
yeah
second,
yeah yeah
yeah, you'll
so
have both
for
kind of
yes
inversions.
yeah you will have both kind of inversion and both will be counted once and so the problem now reduces to find number of paths of length k plus
Yeah,
1
length k. Hmm.
length k yes length yes so the problem now reduces to find number of paths of length k and then multiply it with k plus 1 c2 I guess yes k plus 1 c2 yeah. So this is the standard problem of centroid decomposition that find the number of paths of length k. So find number of paths of length k. So any path A to B will have LCA in between. So we use centroid decomposition. So the idea is so this will be the LCA. So any path of length k So this can be anything. Let it be x. This would be k minus x. So if my starting node is a, and I want to calculate how many nodes b are there, such that its distance would be k. So what I have to only do is uh, this distance would be constant, because this is a particular LCA. So I am iterating over all the ancestors. So I fix an LCA and I want to calculate how many nodes b such b's are there, such that distance from a to b will be k. So let it be x. This is a constant. Now I want to calculate number of nodes which are from k minus x to LCA, right? So it would k minus x. But will it work?
We have the same problem again that this
Yeah.
node may not be the LCA.
Yes.
You may overcount.
Yes.
Mm.
So if this node is also having k minus x, but you will overcount this for this node. So how to deal with this? So in this case, you may realize that the earlier case was on the online. So the earlier case was asking you the queries, but in this case you want the queries for all the nodes. So you can do this offline also. Can you think of some trick which will take this into consideration offline? So the property of centroid tree is that the height is at max log n. So if you make any data structure of each node, which is any data structure like set array, then also it won't be greater than n log n square. Can you use this fact?
Yeah, thinking. Mm.
So you can build any array of this whole tree for all the trees for all this. Can build any set, any array, anything you can do. So what you have to do is just remove the
Right, you only take like the nodes which are not in its subtree. Like
so
you have them in the array. Like
yeah, you have already built the centroid tree and you know how, and you
mm,
know which nodes are there in your subtree and which nodes are not. So you can just, what you can do is, so one solution, so there can be many solutions. So one solution is first build the array of distances for all the nodes in my subtree. So it will include this one also, and then go to each subtree and then uh, first delete all the nodes which are in its component. So in its component means in its subtree, delete them. Delete them means decreasing the frequency or anything. Now the array contains, let's say I have deleted these. Now this only contains the information of the nodes which are having LCA as this node only. Now do your task. What is your task? Calculate the frequency of k minus l, let distance from a to LCA,
after this, it's obvious what to do. Mm.
you know. And
Mm.
then again also you add this and repeat this process for this, and again also you do this. So you build the array for each node, but then also the complexity won't be greater than n log n square. In this case it would be, so that if you build the array then it would be n log n, if you build the set it would be n log n square. But why the complexity won't be greater? Because each node would be present how many times, the number of ancestors it would have, right? Each node would be present in these many times only, log n times. So n log n will be the say space and time complexity. So this is the beauty of centroid tree, that you can build any data structure and it looks naively, but it is not, and it works. So this is the problem now. So finding number of paths of length k. So I will repeat the solution. So what you do is, you first build a centroid tree, which is in NlogN, and then for each node you visit, uh, make the frequency table of distances for all the nodes in its subtree. So let's say these nodes are there. So I will make a frequency table of all the nodes. Then go to its all its corresponding parts, and then erase all the nodes from the subtree, all the distances from the frequency table, and then take the query of all the nodes in this component, and then add again. Do this for all. Now once you are done with this node, go to next node, do this. Go to next node, do this. Overall your complexity would be greater, would be this, and at max it would be this. So it will work. Okay. So
Yeah.
are there any doubts in this question? Okay, so we'll move to this problem.
Are there any standard ones? Like if there are no, like just to practice, then we can skip. Like maybe try only the standard ones.
So I will give you all. There are much more questions. I To practice, I will give you other questions also. So
Hmm.
this is the standard question, which is, so find number of all paths, find number of paths of length k, and find the minimum. These are the standard questions which I am doing.
Hmm.
I will give you more questions to practice. Read this problem. Consider a binary tree which is initially empty. Also consider the first and positive integers and its permutation. If we start adding these numbers to the binary tree, starting from a1, continuing with a2, and so on, ending with an. After every addition, we ask you to update the sum of distance between every pair of these nodes. So we are given a binary search tree which is initially empty, and we are given a sequence. We are given a permutation, and we have to add this permutation to the binary search tree.
Yeah. So
And
we are given a tree already, right?
no, so the tree is empty, so you have to build the tree. Yeah, you are.
But like
Yeah,
what
yeah.
node?
The tree will be unique. Yeah, you are given a binary search tree.
Okay, and you like it's like all nodes are painted black and you have white, then something like
Yeah,
this.
yeah, yeah, yeah. So you build the binary search tree, and you can consider all nodes are painted first white, and then after each addition, you are painting the node black, and what you have to output after each addition, you have to output some of distances between every pair of these nodes. So these nodes means all the nodes which are white or which are black in your case. But you say, so the answer will be affected only by the node which is being added, right? So
We can do the same thing as before, like we did for the K thing. We in each update, we just for each node we just store the sum of distances, and we can and like when we add a node, we go to all of its ancestors and add the sum and plus the number of nodes in other subtrees into the path length, like something like this.
yes.
That should
So
work.
you have to store two things, right? Sum and count.
Count you do not need to store, right?
No,
Because
but no, but for
count will be number of nodes not in its subtree. So
so number of
we
nodes
can
not in it.
obtain that directly.
How? But the tree center. How
Okay,
will?
you need to just obtain like how many nodes are in its subtree for each
No, no, no.
node.
But how many active nodes are there initially?
Oh, okay, okay, okay. You need to store that too.
You
Hmm.
need to store, right?
Hmm. Hmm.
And yeah, yeah. Solution is same. Yeah. So all the problems that we'll seeing now will be of similar kind of thing. So they will be using this property of reiterating or something else. Okay. So I will. explain the solution. So the solution is build the centroid tree first of binary search tree. So first build the BST initially because you are given the sequence. Then build the centroid tree, and the sequence you are given. Uh, let's this be the centroid tree. The sequence you are given, mark each node as initially white, let's say, and now you are making each node as black. So what the problem says is you have to find the sum of distances for all pairs. So the answer will be the previous answer plus sum of distance from the added node, right? Because other pairs we don't touch, so their answer won't change. So we have to just tell what will be the sum of distance from the added node. So let this node be the new node which is being added, and I have to tell sum of distances for all the black nodes only. So what Kumar, what you said will not work because this is like an online query. Do you realize this? Because
No, why not? Why? Oh, yeah, yeah. We have to store count. Yeah.
no, but the whole thing will not work because you will not do the this kind of thing, the array kind of thing for each update, right? Otherwise, it would be nlogn
You
into
don't need to store an array, right? So let's say you are painting a node black. You
yes,
travel to all of its parents
yes,
and you add the sum to the sum count and increase the count also.
no, but how I obtain the distances from these nodes?
Which one? No, like whenever you're given a query, right? Whenever you update a node, uh, then you calculate the distance again, like for all the paths which contain this node. Like,
No, no. Let's assume I have updated the tree and now I am adding a node, right? Let's assume I am adding this
hmm,
node, and
yeah,
these all black nodes are already added.
yeah. So you travel to its
Okay,
parent.
now I travel to this one. Then
Wait, you made this node black, right? Okay. You calculate all the distance to nodes.
to no
You
to the
add some. If
so I add the sum of distances from this node, right?
yeah,
But the same thing will happen that this may contain the nodes which are in this.
that we can subtract. Like while going up, we can just
Yeah,
subtract.
you have to subtract. So
Yeah,
what you
yeah,
need to
yeah.
store to subtract, you should have more information, right? Because the distances from this node to this node will not be like this node to this node plus this node to this node. There's
We need to subtract the subtree count also.
You need to subtract the subtree count. What I'm saying is you need to do other things also, because let's say this is distance b and this is distance a and this is distance c, then b is not equals a plus c. This is centroid tree, so these are the distances in the original tree. This is what I'm saying. If you want to subtract the distances, then you have to store their distances from its parent also. Got it? So you what you want to subtract is the repetitions, and the repetitions will happen from only this tree. So maintain two things. First, the sum of all the nodes, sum of distances of all the nodes from this node, and the second thing is sum of distances of all the nodes from its parent. So when you go to this node, you add the sum of distances to all these nodes minus sum of distances to all its parent of this node. So its parent is this node, and sum of distances all these nodes will be subtracted. So it will have only the sum from the nodes which will give you LCA as this node. Does it make sense?
Yeah, got it.
plus you have to add this distance for how many times the number of black nodes which I am having to other components. So you have to store the number of black nodes also in all the nodes. So it will have the count, let's say C1, and minus this also the number of black nodes which are which is in its subtree. So C2. So you have to add C1 minus C2 into distance from my ancestor comma A. So I will repeat the solution. So the solution is maintain three things. First one is sum from so, uh, sum of distances from centroid to the node, to all the nodes in its subtree. For each centroid we have to store these three things. So first one is this. Second one is count of all active nodes. Third thing is sum of distances from parent of centroid to all nodes in its subtree. So maintain these three things as we have did for the problem one. So maintain these three things. It is easy to maintain. Now for answering the for getting the sum from this node A, visit a vertex which is the ancestor of A and get this first thing. So I will name them. Let it be sum of I, let it be count of I, and let it be sum to parents sum underscore par of I. So for each node I which is the ancestor of A, sum add sum of I minus sum of parent of uh, the next child of I. So let it be ch plus count of I minus count of ch into distance from A to I. So add this sum for all I which are ancestors of A. So this will give you the sum of distances of all nodes which are currently present in the tree. So is it clear? This question BST maintenance. So are there any doubts in this question or should we move on to the another question? Yes, any responses? Why this link is why I'm not able to open this?
No idea. Gym links do not open properly.
No, but I did solve this problem.
Mm. Try opening the like gym code. Remove the problem part. Like copy till the 70.
Okay.
Oh,
not able to see the plus one.
Oh, it's after E problem. Uh, Oh, it opened. It opened.
Hmm. Okay. So let's read it. Deep pressure allows trees. A tree of order n is a connected graph n vertices and minus one edges. Deep pressure also loves queries. Deep pressure has a weighted tree of order n. Each edge has a length. The distance between two vertices is the sum of length of edges between them, and we show it by d of v comma u. Deep pressure asks you to perform q queries. Each query gives you numbers v comma l, and you should tell him the number of vertices like u such that d of v comma u is less than equal to l. So you are given a query, and so you are given a tree, and you are asked q queries about. You are given two things: the vertex and the length l, and you have to tell the number of vertices u which are at max the distance l from it. The constraints are n and q are less than 10 to the 5, and l is 10 to the 14. Yeah, any hints? So you have to tell the number of vertices which are less than or equal to l. So how to solve this? You can also solve this offline.
You can store some. Can I store like ordered set in every node
Yeah,
since
yeah, you can do anything.
hmm,
Yes, I did by ordered set. Yes, you can do any send segment tree or ordered set.
the ordered set is works for this? Yeah, so you go to like you go to a node and just travel all its ancestor, and you need to check like same thing, that what are the nodes which are not in its subtree, which are l minus, which are less than equal to l minus the distance between node and ancestor,
Hmm.
right? So you store an ordered set with all the distances.
But how will you remove the vertices which are
Yeah, that about that.
say I see I can we can do it
It
offline.
will
So
be like something log and
uh,
q n log of.
no, the I think the second question as we did. Can you think in the similar way because we can do it offline. So you can maintain the array, you can delete the current components distances, and then apply the ordered set, and then also update. Can you think in these directions? So we will be solving the problem offline. So what we are doing is we have to tell the number of vertices v from u which are less than or equal to l. So as we did in question 2, we maintain a data structure for each node in the centroid tree. So we will go to this node. We maintain some data structure like, let's say, ordered set, which will contain distances from this node to all its children. So this will contain the distances. Now consider this component. I have to subtract. What I will do, I will subtract the distances from this component. The distances from this node, which will all from this component, I will subtract them. Subtract means I will delete from the ordered set, and then for the query, let this distance be k, since this is a constant. I have to tell the number of vertices which are having distance, let they have distance x. So x plus k
So
to be
you
less
are
than
doing
equal to
like
l.
for every for a subtree, you're solving all of its queries and
Yes,
then
yes, yes,
move
yes.
up, delete it. Okay, okay, got
Yeah,
it.
yeah, yeah. Because we can do offline, so we will we will store the queries in all the nodes, and will so after maintaining this, I can answer all the queries for this component. So I will do this. So I need the dist x to be less than equal to n minus k. So ordered set has a function called, what its name, order of key, right? Order of key, na? What is the name of the function?
Order by key. No, order of key.
Order of key.
Mm.
Yes, order of key. So order of key of l minus k will give me the number of nodes which are okay plus one. The number of, because it gives the strictly less than. So order of k of l minus k plus one will give me the number of nodes which are less than or equal to l minus k distance. And since I've already subtracted these nodes, so all the nodes will have the LC as this. So I will add this to the query of this node. I will do this. I will do this thing for all the nodes, and will add the corresponding queries. So this problem will be solved offline. So is this clear? We
Yeah.
can we can do the segmentary also, but since the weights are 10 to the 9, you have to compress first. So segmentary is not nice thing here. Yeah, so if the problem were like the weights are between 10 to the 5 or 10 to the 6, then the segmentary trick is also good. What you need to do is maintain the segmentary of all the
It will be
weights.
same complexity. Ordered set is just a
No,
nice.
no, yes, but some online judges, I guess, don't allow ordered set. You will get to know when you will sit for internships.
Oh,
That's why.
yeah, but like I like coding
Yeah,
segmentary
yeah,
anyway.
yeah. I get your point. Coding segmentary is a bit heavy. Ordered set is a nice technique, but as an alternative ordered set, I'm suggesting segmentary can also be used. That's what I'm saying. Okay. So what was I saying is, if you want to do by segmentary, you just maintain a frequency table of distances. So mark the distances. So count. So increment the frequency of the vertices which are there in your subtree. And then for answering l minus k, just take the sum from this to l minus k. So this is when the distances are from 10 to the 6 or 10 to the 5 or 10 to the 7, so that you can maintain the segmentary. But here the distances are very large, so segmentary won't work directly. It can work, I guess, by using some compression, but directly it won't work. So the ordered set is fine here. Okay, so is the problem clear, or are there any doubts in this problem? Okay, we will move to another problem. So this is very easy problem. So this is just the illustration of why centroid decomposition is useful. So read the problem. Now Foxhill becomes a commander of Treeland. Treeland, like its name said, has n cities connected by n minus one and directed routes, and for any two cities there always exists a path between them. Foxhill needs to assign an officer to each city. Each officer has a rank, a letter from A to Z, so there will be 26 different ranks, and A is the topmost, so Z is the bottommost. There are enough officers of each rank, but there is a special rule must obey. If X and Y are two distinct cities and their officers have the same rank, then on a simple path between X and Y, there must be a city Z that is an officer with higher rank. Okay, the rule guarantees that a communication between same rank officers will be monitored by higher rank officer. So the problem is you are given a tree, and you have to for each vertex you have to assign an officer. An officer is a letter from A to Z, and you have only one rule that for each city, for
This is just build a segment tree. Sorry, build a tree use with height uh, less than 26, right?
sorry, did you get the question?
Yeah. Once no.
Okay, so let me repeat. Let me complete the question. So you are given a tree, and you have to assign for each vertex a letter. And there is only one rule that for any two vertices present on the tree, uh, there must be a letter which is greater than. So there must be a letter in the simple path from A to B which is greater than this letter. So you have to ensure for all the paths that there must be a letter which is greater than this letter.
Create
So
the segment tree and like assign like height one assign. Uh,
segment tree.
no, no, sorry,
Okay,
centroid tree,
centroid tree.
centroid tree.
Yes, yes, yes.
Like assign higher ranks to top and like in
Yeah,
a
yeah, yeah. So think how it is easy with centroid tree. How it is so easy.
yeah.
Now think what we can do without centroid tree. How will this? It's different. See, that's why, because if you don't know centroid tree, then it would be very. It won't be that much easy. So we have to ensure for every part that there must be a node which is present, which is greater than this. So I don't uh, know what to do without centroid tree. And this question explains the power of centroid tree. So I will explain the solution. So the solution is same as what Kumar said.
Wait 1 second. Without segment, can you show the question once?
Okay, so I don't know the solution. I was just asking you to think, and you'll
One
get
second.
how. Yeah. Okay, you can try without centroid tree. Yes, maybe there may exist some solution.
Yeah, you can change.
Okay.
Red.
So the solution is build the centroid tree and give higher ranks to. So give the ranks as the levels. Give higher ranks to them, the topmost, and then low rank to others. Since the number of nodes are and the height would be less than log n, less than or equal to. So it is less than 26. So you can assign level by level labels. So let's say 8 a to sorry z to this, y to this, x to this, and so on. So you assign the labels by levels. Okay, A is the topmost. So A to this, B to this, C to this. That way, you ensure that because any two nodes, their LCA will be present in the path from A to B, and the LCA is having the higher rank. So you ensure that for any two nodes, there will be a node which is present in the path, and it is having the higher rank. So this is only one line code after the code of Centroid tree, and it's div1c. So it's 2100 rated. So are there any doubts in any question? So we are done with all the problems. If you have any doubt in any question or in any part of the topic, you can ask now. Okay, so thank you for joining the meet. If you still have any doubts, you can ask, or we will end the meet.
Yeah, post the resources on the Discord, sir.
Yeah, so I've already posted the doc of questions. I will also keep some more questions for practice, and we'll post the resources on Discord and the event link in the event post. Okay.
Yeah,
You want you want these questions only, right? This slide is useless.
this one you said some more questions you have.
Yeah,
These,
yeah, 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 yeah. These five and some more questions.
yeah, these already.
Yeah, yeah. I will prepare the doc and I will share them on the Discord and the event also.
Hmm.
Okay, so if you have any doubts, you can ask, or we'll end the meeting.